and MAB3 do not exhibit geometrical isomerism. We shall now discuss geometrical isomerism in complexes with coordination number of 6. These complexes possess an octahedral geometry. Consider the complex MX2L4. The two X ligands may be oriented either cis or trans to each other. Say for example, in cis-D-amine tetracyanoferrate ion, the identical ligands NH3 are situated at an adjacent position, while in trans-D-amine tetracyanoferrate ion, identical ligands, that is NH3, are situated at the opposite position. Now consider the case MX2LL2, where L is the D-dentate ligand. When the X ligands are oriented adjacent to each other, the isomer is designated as cis. However, when they are oriented opposite to each other, the isomer is designated as trans. Say for example, cis-D-chloro-D-N-cobalt 2 and trans-D-chloro-D-N-cobalt 2. In octahedral complexes of the type MA3B3, another type of geometrical isomerism is observed. For example, in triamine trinitrocobalt 3, if three identical ligands occupy one face of the octahedron, it is called facial isomer. This complex is called facial triamine trinitrocobalt 3. If in the same complex, three ligands are not in one face of the octahedron, meridional isomer results. This complex is called meridional triamine trinitrocobalt 3.
Relation between geometry and magnetic properties of transition in metal complexes. Objective: to study the geometry and magnetic properties of tetracyanonickelate 2, NiCN4 2-. In the NiCN4 2- complex, Ni2 plus ion accepts 4 electron pairs donated by 4 strong Cn- ligands and thus has a coordination number of 4. We know that a complex with a coordination number 4 can have either tetrahedral or square planar geometry. Let us first consider the possibility of tetracyanonickelate 2 having a tetrahedral geometry. The outer electronic configuration of Ni2 plus ion is 3d8. We have studied that in order to form a tetrahedral complex, a metal ion must undergo sp3 hybridization. Consequently, the unoccupied 4s and 4p orbitals of Ni2 plus ion intermix to produce a set of 4 equi-energic sp3 hybrid orbitals. Each cyanide ion now donates an electron pair to the Ni2 plus ion. These electron pairs get accommodated in the 4 sp3 hybrid orbitals of Ni2 plus ion. NiCN4 2- thus formed contains 2 unpaired electrons. Hence, it is paramagnetic, that is, it gets attracted by a magnetic field. However, experimental studies confirm that NiCN4 2- is diamagnetic. That is, it is not attracted by a magnetic field. Hence, this complex cannot have a tetrahedral geometry. Now, consider the other possible option, which is the square planar geometry of tetracyanonickelate ion. To form a square planar complex, a metal ion must undergo dsp2 hybridization. This necessitates the rearrangement of the 8 electrons in 3d orbitals of the Ni2+ ion. The strong Cn- ligand causes the 2 unpaired electrons of 3d orbital to pair up, leaving one 3d orbital vacant. This vacant 3d orbital, as well as the 4s and 2 of the 4p orbitals, now undergo hybridization, resulting in 4 equivalent dsp2 hybrid orbitals. The 4 cyanide ions donate 4 electron pairs to the Ni2+ ion, which get accommodated in these dsp2 hybrid orbitals. NiCN4 2- ion, thus formed, has all its electrons paired. Hence, it is diamagnetic. This proves that NiCN4 2- is a square planar complex with dsp2 hybridization. Summary: we have seen that NiCN4 2- is a diamagnetic complex with a square planar geometry and dsp2 state of hybridization.
The color of transition metal ion complex is 1. For a compound to be colored, the metal must have incompletely filled d orbitals. Almost all transition metals have incompletely filled d orbitals. For example, vanadium has an outer electronic configuration of 4s2 3d3. Chromium has a 4s1 3d5, whereas iron has 4s2 3d6. Let us consider a copper atom as an example. It has an outer electronic configuration of 4s1 3d10. There are no vacant d orbitals in copper atom. But if copper gets oxidized by losing 2 of its electrons, one of the d orbitals becomes half-filled, and therefore all the compounds in which copper exists as Cu2+ are colored. In case of zinc, which has an outer configuration of 3d10, 4s2, there are no empty d orbitals. Even when it forms Zn2+ ion, the electrons are lost from 4s orbital, leaving completely filled 3d orbital intact. Hence, the compounds of zinc are colorless. It is thus important for a metal or its ion to possess empty d orbitals in order to form colored compounds. Let us now understand the significance of empty d orbitals in perception of color. When solid copper sulfate is dissolved in water, it dissociates into cupric and sulfate ions. The 3d sublevel in cupric ion has 9 electrons arranged in 5 degenerate orbitals, that is, orbitals having equal energy. The ligands, that are water molecules, approach the copper ions and form 6 coordinate bonds. Thus, hexa-aqua copper 2 ion is formed. This bonding splits the 3d orbitals into 2 different sets of sublevels, in which 2 occupy a higher energy level than the other 3. The magnitude of splitting of 3d orbitals depends on the oxidation state of the metal and the nature of the ligands. When light passes through a solution of these ions, some of the light energy is utilized to excite an electron from lower energy level to a higher energy level. This amount of energy required to excite an electron corresponds to the energy associated with a particular wavelength of light. In the case of hexa-aqua copper 2 ion, This energy corresponds to the wavelength of 605 nanometers of the visible spectrum, which corresponds to red light. This means the light coming from the other side will have all the colors of the spectrum except red. The mixture of the wavelengths of all the colors appears greenish-blue to our eyes, and it is the complementary color of red. Hence, copper sulfate appears greenish-blue to our eyes. Although we have to keep in mind here that this mixing of wavelengths is not the same as mixing of paints or pigments of the same color. To summarize, we can say that the color of a metal-ion complex depends on the presence or availability of empty d orbitals in it. Bonding with ligands leads to splitting of d orbitals having unequal energy. Absorption of energy from light excites the electrons from lower energy sublevels to higher energy levels. The amount of energy absorbed corresponds to a particular wavelength of light in the visible spectrum. A wavelength of color complementary to the absorbed wavelength is transmitted, and our eyes perceive that specific complementary color.